So this video will go over some example problems of solids or revolutions, specifically using disks to evaluate the volume of an object created by revolving a curve around an axis. So our first example here says we need to find the volume obtained by rotating the curve y equals x cubed about the y-axis on the given interval. So the first thing we should obviously do is draw that function. Now what I know right away is if I'm going from 0 to 8 on the y-axis, that implies that we're just going from 0 to 2 on the x-axis. So that curve, I don't really care what it looks like down there, but that's x cubed, so therefore that this point here then is going to be 2, and then where that meets, this point here will be 8 on the y-axis. So I just made a quick little sketch of that. I'm going to clear up the rest of the curve that I don't need to see anymore. So what we're going to do now is we're going to rotate this about the y-axis. So let's draw a picture of that. So here, that would be flung all the way around. This point would come around. This point would come around. So we can see here is we see a bunch of disks. I'm going to draw 1 or 2 representative disks as best I can. And then, like, let's say that's that disk, and I have a smaller disk down here that kind of looks like this, which is, again, pretty hard to see here. What we notice is that each disk has a changing radius, which means in our notation, this little distance here, right, the width of that, or in other words, maybe we call that the height of those little disks, that is something that has nothing to do with the function. That's something that, so this distance that I'm talking about, this will go to 0, because if we're trying to get a bunch of those disks in there, an infinitely many, or an infinite amount of those disks, we need to get them thinner and thinner and thinner. Now, because this is an up and down direction, I'm going to call that just the change in y for those disks. So if we wanted to calculate the volume of the image that was, or the shape that was created by rotating this around, so if I wanted to just kind of sketch that, it would look something like, this type of figure here. So if I wanted to calculate the volume of that figure, the volume, what we're going to do is we're going to add up an infinite number of those disks. So each disk will have its own volume. So the volume of those disks will be pi times whatever its radius is, squared, times the height of those disks. So what we see now is that the height of those disks, that's what we said right here, that's going to be the change in y, because that's going to go to 0. Now, as soon as we say that that y value is going to go to 0, we're then implying that we're using an integral. And the height is going to go from 0 all the way up till 8. Now, what we need to do is we need to think about how that radius is going to be squared. Now, what we notice here is that the radius of all these disks is just the x value of that curve. So this is like the radius of 2. This radius right here would be 1. So I want to represent this radius in terms of y, though, just because that is the variable of integration. So I happen to have this formula that y and x are related. So I want to get the x value, again, because the radius of each of those is just wherever we are on the x-axis. So like this radius, we're 2 on the x-axis. This radius is whatever that number is on the x-axis. This radius is 1. So I want to rewrite this equation to get the radius, which we know is x, alone. So I would just take the cubed root. So the cubed root of y would equal the x value. And that's what we're saying. The x value is the same thing as the radius of each of those disks. So that's why I'm going to choose to input the cubed root of y, just because we always want to make sure that our variable of integration matches the variable that we're actually using. And then again, we can also verify that it matches the limits of integration here on the y-axis from 0 all the way up till 8. And then from there, we're just going to integrate. So I'm going to rewrite the function. So I'm going to square and remove the pi. So from 0 to 8 of y to the 2/3 power in this situation. And then times dy, which will give us pi. We can evaluate this integral by adding 1. So that's where we get the 5/3, all divided by 5/3, and we're evaluating that from 0 to 8. And then from here, again, I'm just going to rewrite this as 3/5, and if we're going to evaluate 8 to the 5/3 power, and then we distribute that pi. So 8 to the 5/3 power would do the root first. So the third root of 8 is 2. 2 to the 5th power is 32. So we have 3/5 of 32 pi. Which we can just represent as 96 pi over 5, and whatever the units would be since it's volume, it's cubed. So let's do one more problem. So here we're supposed to find the volume obtained by rotating the curve y equals sine of x cosine of x about the x-axis on this given interval. And it says that we could use a calculator. So the first thing we should do, of course, is just draw that function. So on the x-axis, we're going from 0 to pi over 2. Now, since we're given a calculator here, all I'm doing is I'm just taking out a calculator, and I'm just looking at that function on the interval from 0 to pi over 2. And what we see is it's going to create a pretty characteristic portion of a period here. So it looks like that. And again, since we're given a calculator, we can use the calculator to get that image. So what we're going to do now is we're going to rotate this image about the x-axis. So like this part in the middle here is going to come at me, and then it's going to be swung around the backside. So this has the biggest radius. Now something here, those discs are obviously going to be a little bit smaller. Like maybe here, it's going to come at me, and it starts rotating away from me. Something like right down here, this disc would be a lot smaller. So what we're seeing here is that the discs start to look like this. I'm going to draw 2 of them. So one of them could be like really, really, really tall. Like we'll do that first one. So if we did that first one here, it's really tall. And we're seeing like between the next disc, like maybe like this one here, it's just really short. But we are noticing that the width of those things here, this thing here, and that is the same. So we're noticing that our radius changes. And what I'm calling the width in my orientation right now is arbitrary, meaning it's going to go approach 0 because we're going to try to fit as many of those disks as we possibly can. So it just helps me orient my variables. So if we're going to find the volume of the entire figure, we're going to add up a ton of volumes of each of those disks. So the volumes of each of those disks will be pi times its radius squared times whatever the height is, or in my case, I'm now calling that the width here. So the width is whatever arbitrary distance I set between them, and that's on the x-axis. We're going to change things in terms of x. Now, because this width, as I just said right here, this is an arbitrary width that we're going to eventually have get closer and closer to 0, so we can get more and more disks in there. That implies that we're now using an integral, and since our variable of integration is the x-axis, we're going to go from 0, which is where we start, all the way to pi over 2. What we need to make sure of is that when we represent the radius of each of those disks, that radius is in terms of x because that's the variable that we're given. And what I want to note here is like if I just choose a radius, this radius right here is just the function's value, right? So that is y if I put in an x value. So what I do see here is this radius is in terms of x already. So I can call that sine of x, cosine of x. And then here, since we're told to use our calculator, I would just go ahead and use the calculator function of the integral to evaluate this. And we should get something incorporating the pi, some sort of decimal representation as like 6.17, whatever the units would be. Since it's volume, it is cubed.